students, welcome to nuclear physics lecture. I'm Dr. Pervez Ahmed. In this lecture, we will talk about the second part of the liquid drop model. You know that uh, in the previous lecture, we discussed about the first portions of the liquid drop model. And that first portion, we discussed about the surface energy. We discussed about the volume energy term, and then we discussed the surface energy term that contributes to the total binding energy of the uh, nucleus. Now, in these lectures, we will continue with the Coulomb energy term. So, what's Coulomb energy term? Just like you can see it here in this particular figure, that is, you can easily observe here that the electric repulsions between each pair of the proton in a nucleus contributes toward decreasing its binding energy. That is, you can see it here by yourself. That is, in these red color, these are the ball that represents the nucleons, that is protons, and these protons they have the opposite charge. So the opposite charge, you know that sorry, they have the positive charge. So the positive charge mean that they have the same charge, they repel each other. So just because of that fact, we say that it contributes towards decreasing its binding energy. That is, let me repeat it again, the electric repulsions between each pair of the protons, that is, you can see it here, we have different pair of the proton. So it contributes toward decreasing its binding energy. So the basis for this term is the electrostatic repulsion between the protons. I mean, the Coulomb energy term. When we are saying something about Coulomb energy term, so it means that this term is the electrostatic repulsions between the protons inside the nucleus. So now there is a basic, well-known fact which almost each of you people know, that protons and photons have repulsions, and these repulsions make nucleus less tightly bound. I mean, you all people know that in the nuclei we have the only charged particle as the neutrons, or in the form of neutrons. We have the only charged particle, that is protons, and you know that these protons they have the same charge, and the same charge they repel each other. So protons repulsions make the nucleus less tightly bound, uh, and this kind of the repulsions that we call Coulomb repulsions. You know that just like the range of the electromagnetic force, as we have discussed in the previous lecture, this is basically a long distance Coulomb refulsion. Here you can see that in between we have the other particle, that is neutrons. But neutrons, they are electrically neutral particles, so they do not contribute to electrical refulsions among the proton. So the long distance Coulomb these repulsions between the protons are long distance, or we can say there is long range repulsions between the protons, and this kind of repulsion basically need to reduce binding energy. So just like we discussed previously, that is means that we have pairs of the protons, that is protons pairs. So we need to calculate how much, I mean, the proton pairs they contribute to binding energy. As we discussed that proton repulsions make nucleons less tightly bound. So let us assume that protons, if we say that there are that protons in a particular nucleus, so the question is how many protons pairs. So for that we have to utilize the relation, that is z factorials divided by 2 factorials into z minus 2 whole factorials, which equal to z n2 uh, z minus 1 divided by 2. You remember here we utilize z for the number of the photon. So Coulomb energy is proportional to 1 over r. That is, we can say that Coulomb energy is inversely proportional to the separations between the nucleons, which is protons, which are protons in this particular case. Uh, Therefore, we can say that this is proportional to uh, a raised to power minus 1 by 3. So the Coulomb energy term to the binding energy in this particular situations is equal to minus AC n2 z n2 z minus 1 whole divided by a raised to power 1 by 3. So this is the Coulomb energy terms we have. Uh, what about the asymmetry energy? So the in the case of asymmetry energy, we can start a discussion like the most stable form of the nucleus matter would have equal number of the neutrons and protons. I mean, whenever we're trying to discuss about the asymmetry energy of a particular nucleon, so we assume that that particular nucleons, if we say that we should have the most stable form of nuclear, and we are interested in that kind of nuclear, there should be a fact we should remember, that is the most stable form of the nuclear matter would have number of neutrons equal to number of the protons, uh, and unequal values of the neutron and protons imply feeling higher energy levels for one type of particles, while leaving lower energy level vacant for the other type. I mean, this fact you can see, you can see it for yourself. I mean, if you assume the lower energy level and the higher energy level like this, so here, I mean, the red particles, they are basically denotes the protons, just like you can see here in this particular ways, and the number of neutrons, and the blue colors you can see it here. So this is the first case, and this is the second case. I mean, and first case we are saying that what was the probability here? We assume that the most stable form of the nuclear matter would have equal number of neutron and protons. So this is the first possibility. The second possibility is unequal values of neutron and protons implies feeling high energy levels for one type of the particles. This for one type of particles, while leaving lower energy level vacant for other type of particles. So this is the second possibility. What we have next? Uh, this symmetry, here we say we have the symmetry. So this symmetry will also reflect in the binding energy of the system. So how it be? Let we assume that proton and neutrons, being distant type of the particle, they occupy different quantum states. I mean, it's a well-known fact. So one can think of two different pole of states, one for the protons and one for the neutrons. So now, for example, if there are significantly more neutron than proton in a nucleus, so some of the neutrons will be higher in energy than the available states, and the protons fall. The imbalance, between uh, the number of protons and the neutron causes the energy to be higher than it needs to be for a given number of the nuclei. So how we have the asymmetry term for the binding energy. So as we mentioned on the previous slide, light stable nuclei tend to have approximate equal number of proton and neutron, which tend to A by 2, that is the total mass is divided by 2, that is we have equal number of neutron and equal number of proton. So this means that as the atomic mass increases, so there is more protons Coulomb repulsion. So a number of neutrons is greater than proton. If we say that number of neutron greater than number of proton, so imbalance between neutron and proton can lead to the asymmetry term. I mean, here you can see it here by yourself. That is the symmetry term to binding energy is equal to minus a s y. The subscript sign is basically for the asymmetry, uh, and 2a minus 2z whole square divided by a. And here you can see that it reduces the effect as a increasing. So you might have observed this particular fact. So let's come toward the fairing energy terms. What is fairing energy term, or what is mean by the fairing in the case of liquid drop model? So it's been observed that in uneven in even number of particles is more stable than an odd number. I mean, this is when we trying to explain the concept of fairing according to the liquid drop model. So it must be noted that an even number of particles is more stable than an odd number. So due to Fall exclusion principle, the nucleus would have a lower energy if the number of the proton with the spin up will be equal to the number of proton with the spin down. This is what the Fall exclusion principle say about the fairing of the nucleus inside the nucleus. So this is also true for the neutrons. I mean, neutrons they also have a spin. So I mean, Fall exclusion principle is equally applied to the neutron as well. So only if both proton and neutrons are even, both proton and neutrons can have equal number of spin up and spin down particles. This is similar effect to the asymmetry term. So let's summarize the fact for the asymmetry term, that is even nuclei are particularly stable. Uh, Proton number equal even number of protons and even number of neutrons. Or our nuclei tend to be unstable, that is if we have particular type of nuclei in which we have odd number of uh, proton, odd number of neutron, so that kind of nuclei would tend to be unstable. So that this fact we later on we will discuss in the shell model. So the pairing term here in this particular conditions will be equal to plus minus delta. So plus minus delta is basically depend upon the number of the total number of nucleons and the total number of the proton. So what it mean? It mean that for even I mean even number of neutron and even number of protons, the delta term will be positive. And for the odd terms, the delta term will be 0. But for the odd and even terms, it will be negative. That is, for odd and even number of proton and neutrons, the delta term will be negative. So the pairing term will be proportions to a raised to power minus 3 by 4. That is, b pairing term will equal to a the subscript pair and 2 a raised to power minus 3 by 4. So this is the pairing term to the binding energy. So if we combine if you combine the total terms to the binding energy, so we will have the total binding energy in this particular form. That is, we combine the contributions to all the terms. This is the contributions due to the volume term. This is due to the surface term, Coulomb terms, asymmetry term, and the fairing term. I mean, if we combine all these contributions, so we get this formula, and this formula for the bending energy is called semi-empirical bending energy formula. This is semi-empirical bending formula. So according to this formula, it's uh, this formula best fit to experimental binding energy curve yields. That is, it can have the value here. I mean, it best fit the for the value. We can have these values. That is for surface energy for AV. We have the value of 15.5 mega electron volt. For surface, we have the value 16.8 mega electron volt. For Coulomb energy, the value is 0.72 mega electron volt. For asymmetry, sorry, for symmetric, we have 23 mega electron volt, and for fairing, we have it 34 mega electron volt. So this is the value. These are the values. Which best fit and this semi-empirical mass formula. I mean, these are the values of these particular are constant. That is the constant in case of volume term, uh, Coulomb term, surface term, asymmetric terms, and a fairing term. I mean, these are the best fit experimental binding energy curve yields. So that's all we have for this lectures. See you in third portion of this lectures. Till then, bye bye.